For years, Kubernetes Ingress has quietly powered the external entry points of applications all around the world. And even today, Ingress remains an essential part of many platforms. But the ecosystem has grown. Architectures have matured, and organizations now run dozens, sometimes hundreds of microservices inside a single Kubernetes cluster. At that scale, the old networking model begins to feel stretched. Annotations start to appear everywhere. Controllers rely on vendor specific behavior. Infrastructure teams and application teams are tightly coupled in ways that slow everyone down. And the moment you move beyond a simple HTTP routing, the limitations start to surface. That's why exactly the Kubernetes community stepped back and designed something new. Not as a replacement overnight, but as a cleaner, more expressive foundation for the future. Something more scalable, something more structured, something built for the next decade of cloud native architectures. This is the Kubernetes Gateway API, the evolution of Ingress. Ingress was brilliant in its simplicity, but over time, that same simplicity began to turn into a bottleneck. As more teams tried to expose more applications, a few cracks started to appear. And eventually, three major problems became impossible to ignore. The first issue was annotations. Ingress relied heavily on them, even though annotations were never designed to carry routing logic in the first place. Every time you needed a rewrite rule, rate limiting, or custom headers, you weren't really writing standard Kubernetes configuration anymore. You were writing vendor specific extensions. nginx had its own syntax, Traefik had another one, HA-proxy, Kong, Ambassador, each controller spoke a slightly different dialect. Portability suffered, and so did consistency. The second issue was separation of responsibility. Ingress offered no real way to separate infrastructure concerns from application concerns. Platform teams managing shared load balancers were forced into the same configuration files as application developers who just needed simple routes. In large organizations, this quickly became unmanageable. Teams could override each other's rules without even realizing it. And the third limitation was protocol support. In practice, Ingress was almost entirely HTTP focused. If you needed TCP or UDP or reliable gRPC support, you had to bolt on additional tools, each with its own APIs, controllers, and lifecycle. Taken together, these weren't small inconveniences. They were structural limitations. The Kubernetes ecosystem needed something more expressive, more modular, and far more future-proof. And that need set the stage for a new way of thinking about traffic at the edge of a cluster. So, with the problem clearly understood, the next question becomes obvious. What exactly is the Gateway API, and how is it different from what came before? Gateway API isn't just a replacement for Ingress. It's a complete rethinking of how traffic should enter a Kubernetes cluster. Instead of relying on a single object that tries to do everything at once, Gateway API introduces a layered architecture, with each layer carrying a very specific responsibility. At the top of that structure sits the Gateway class. This is where capabilities are defined. It describes what kind of traffic infrastructure you are using, whether that's nginx, envoy, HA-proxy, Istio, or a cloud provider's managed load balancer. The Gateway class sets the rules of the game before any traffic ever flows. From there, a gateway is created. This represents the actual entry point into your cluster, the physical or virtual load balancer that the outside world connects to. It's the shared front door, designed once and reused safely by many teams. Underneath that, you have routes, objects like HTTP route, TCP route, UDP route, and gRPC route. These are where application teams express intent, how traffic should be matched, and where it should be forwarded, routes that attach themselves to a gateway without ever modifying it. And this is where the real brilliance shows up. Gateway API doesn't treat routing as a flat configuration file. Instead, it creates a layered model where infrastructure teams, platform teams, and application developers each operate at the right level without stepping on each other. It brings structure where Ingress brought flexibility, separation where Ingress compressed everything into one file, and clarity where Ingress relied on vendor-specific behavior. Gateway API turns traffic management from a collection of clever tricks into a clean, intentional architecture. To really understand the Gateway API, it helps to shift your mental model slightly. Instead of picturing a single entrance, imagine your Kubernetes cluster as a large building with multiple wings. At the very top of this model sit the infrastructure teams. They define something called gateway class, which is essentially the blueprint for how doors into the building should be constructed. That blueprint might describe an nginx based data plane, an envoy proxy, or even a managed cloud load balancer. What matters is that the gateway class defines what's possible. It sets the capabilities around TLS, routing features, supported filters, and overall performance characteristics. From that blueprint, a gateway is created. This gateway is the axial doorway clients use to enter the building. It defines listeners, things like ports, protocols, host names, and TLS configuration. But here is the key point. At this stage, the gateway still knows nothing about your applications. And that's not a limitation. It's a deliberate design choice. Instead, application teams define routes. Objects like HTTPRoute describe exactly how traffic should behave. Which host name to match, which path to route, which filters to apply, and which backend services should receive the traffic. Those routes then attach themselves to the gateway, without modifying the gateway itself. What emerges from this is a very clean separation of responsibility. Infrastructure teams manage the gateways and its capabilities, application teams manage their own routes, and Kubernetes continuously reconciles the relationship between the two. The result is a model that feels natural. It scales cleanly, and perhaps most importantly, it aligns with how real organizations actually build and operate platforms. If Ingress had a hidden flaw, it was this. You could never truly declare what kind of load balancer or proxy you wanted to run. You installed an Ingress controller, and from that point on, everything depended on how that controller chose to interpret your YAML. The intent lived in your configuration, but the behavior lived inside the controller. The Gateway API addresses this head-on with GatewayClasses. They provide a formal, explicit way to define the data plane your cluster should use. A gateway class describes very clearly which controller is responsible, what capabilities it supports, which configuration options are exposed, and how any gateway created from that class will behave. It helps to think of a gateway class as a preset for your traffic layer. Before anyone steps through the door, you decide what kind of door you are building. Is it glass or metal? Manual or automated? Open to everyone or carefully guarded? Once that choice is made, every gateway created from that gateway class inherits those characteristics. The behavior becomes predictable, consistent across environments, and far less dependent on controller-specific quirks. In that sense, gateway classes give Kubernetes something Ingress never really had: a standardized, first-class way to describe the networking implementation itself, not just the routes that sits on top of it. With the Gateway API, the gateway object becomes the literal front door into your Kubernetes environment. If the gateway class defines what kind of door you are building, the gateway is the physical door itself. The load balancer, the listeners, the TLS termination point, and the shared entry where external client begins their journey into the cluster. A gateway can expose one listener or several, depending on what the platform needs to support. Each listener defines how traffic should arrive, which host name to match, which protocol to handle, which port to listen on, and whether TLS should be terminated right at the edge. By designing gateways as shared infrastructure objects, Kubernetes introduces a powerful idea: multi-tenant gateways. A single gateway can safely serve many teams, each attaching their own routes without ever modifying the gateway itself. This is a fundamental shift from the Ingress model. With Ingress, multiple teams often ended up editing the same object, hoping their annotations and rules wouldn't collide. With Gateway API, that risk disappears. Gateways become the contract between infrastructure teams and application teams. Once the gateway exists, application teams don't touch it. They simply attach their routes to it, like plugging into a pre-built power source that's already been approved and secured. It's control with clear boundaries, structure without rigidity, a shared front door designed once and safely reused by many. Where gateways define entry, HTTPRoutes define intent. They describe very precisely how incoming traffic should be matched, filtered, and ultimately delivered to back-end services. An HTTP route can express exactly what an application needs. It can specify which hostname it applies to, which paths should match, which method or header should be inspected, and where the traffic should be sent, including weighted distribution across multiple backends. This is where the Gateway API becomes dramatically more expressive than Ingress. Instead of relying on controller-specific annotations, the API provides first-class fields for these behaviors. If you want to rewrite a path, there is a field for that. If you need to manipulate headers, there is a native way to do it. Redirects are built in. Traffic splitting is supported directly. Everything that previously had to be squeezed into annotations is now part of the API itself, structured, typed, validated, and portable across controllers. As a result, HTTP routes bring clarity to an area where Ingress often relied on tribal knowledge. They allow developers to express routing behavior precisely and safely, without stepping into infrastructure territory. If HTTP routes are the heart of routing, then filters are very much the soul. They are what allow you to shape, transform, and enrich requests as they move through the edge of the cluster, and crucially, to do it in a standardized, portable way. Filters sit directly in the request path. As traffic flows through, they can rewrite URL path, modify requests or response headers, perform redirects, enforce timeouts, inject authentication requirements, or even influence how traffic is handled before it ever reaches the backend service. What makes this particularly powerful is how different it is from the old Ingress world. With Ingress, these behaviors were usually implemented through annotations, controller-specific extensions that behaved differently depending on what was running underneath. With the Gateway API, filters are first-class citizens. They are part of a shared, well-defined schema that is consistent across the ecosystem. That means a route using filters or header rewrites or redirects behave the same way, whether your data plane is nginx, Traffic, Envoy, or a managed cloud controller. In that sense, filters bring elegance to what was once a messy, annotation-driven landscape. They are the key to predictable behavior, clean abstractions, and truly controller-agnostic networking at the edge of Kubernetes. One of the biggest limitations of Ingress has always been its narrow focus on HTTP. If your application spoke TCP, you were largely on your own. If it is relied on UDP, there simply wasn't a clean answer. And while gRPC technically runs on HTTP too, support across different Ingress controllers was often inconsistent and unpredictable. The Gateway API changes that story entirely. With objects like TCP-Route, UDP-Route, and gRPC-Route, the API introduces a clear, standardized way to route any protocol, not just web traffic. This doesn't just add new features, it future-proofs the entire Kubernetes networking model. Suddenly, database traffic, game servers, streaming workloads, telemetry pipelines, low latency services, and high performance RPC systems can all be routed through the same unified API. In that sense, the Gateway API elevates Kubernetes beyond an HTTP only router. It turns it into a true multi protocol traffic management platform designed for real world production scale systems. One of the most powerful ideas in the Gateway API, and one that finally addresses a long standing pain point with Ingress, is cross namespace routing. With the Gateway API, responsibilities are clearly separated. Infrastructure teams define and own the gateway. Application teams create their own routes right inside their own namespaces. Those routes can then attach themselves to the shared gateway without ever touching the gateway's YAML. What this creates is a natural, secure contracts between teams. No more sharing a single Ingress file. No more accidentally overwriting each other's rules. And no more mixing platform concerns with application concerns. A team building an auth service can define an HTTP route in their namespace and bind it to the shared gateway. At the same time, a team working on a payment service can do exactly the same thing, without either team needing access to the gateway itself. This mirrors how large organizations actually work. Teams own their services, platform teams own the shared infrastructure. And for the first time, Kubernetes models that structure natively. Cross-namespace routing isn't just a technical improvement, it's an organizational breakthrough. One of the biggest architectural wins with the Gateway API is how it approaches advanced traffic strategies. Not through vendor-specific annotations, not through controller magic, but through clean, standardized fields that behave the same way everywhere. Traffic splitting becomes a native capability. You can direct 90% of traffic to one backend and then 10% to another, using nothing more than a simple weight definition. That makes canary deployment straightforward and predictable. A new version of your application can receive small, controlled trickle of traffic, while the stable version continues to serve the majority of users. As confidence grows, the weights change. 10% becomes 20, then 40, then 60, until eventually the new version fully replaces the old. There are no ad hoc annotations here, no hidden behavior buried inside a controller, just declarative, transparent routing that does exactly what it says on the page. And this isn't limited to canary releases. The same weighted routing enables A/B testing, regional rollouts, premium tier isolation, and progressive delivery strategies. In the past, patterns like these often required a full service mesh or a proprietary API gateway. With the Gateway API, they move into the core Kubernetes networking model itself. That makes them accessible to every cluster, every team, and every compliant controller without introducing unnecessary complexity. It's tempting to think of the Gateway API as a straight replacement of Ingress. But that framing misses the bigger picture. Ingress is still widely used, widely supported, and absolutely the right choice for many workloads today. It's familiar, battle-tested, and perfectly capable when your needs are straightforward. What the Gateway API represents isn't a rejection of Ingress. It's a step forward in maturity. Ingress was built with HTTP routing at its core. Gateway API expands that model into a true multi-protocol traffic management. Ingress relies heavily on annotations to express advanced behavior. Gateway API brings those capabilities into first-class, well-defined fields. Ingress tends to compress infrastructure and application concerns into a single configuration. Gateway API deliberately separates them, giving platform teams and application teams clear, independent domains of control. And where Ingress can struggle as organizations grow and routing becomes more complex, Gateway API embraces multi-tenancy and shared infrastructure as a core design principle. Seen this way, the story becomes much clearer. Ingress solved the problem of its time. Gateway API is designed to solve the problem of ours. The two can and will coexist. Many clusters will happily run both side by side for years to come, but the architectural direction is clear. As system scale and demands increase, Gateway API becomes the more reliable foundation to build on. Another question engineers often ask is this: if I'm already using a service mesh like Istio or Linked, do I even need the Gateway API? The answer becomes much clearer once you understand the boundaries each one is designed to cover. Service meshes focus on east-west traffic, the internal communication between pods inside the cluster. They handle things like mutual TLS, retries, circuit breaking, deep observability, and advanced traffic shaping between services. The Gateway API, on the other hand, focuses on north-south traffic. It defines how the outside world enters the cluster. Gateways, listeners, routes, and filters shape requests as they cross the boundary from the public internet to Kubernetes. In practice, these two layers often work together. Some service meshes even implement the Gateway API as their external front door. And in some setups, the same underlying data plane, often envoy, is used for both. But they don't replace each other. They complement each other. The Gateway API secures and controls the entry path. The service mesh secures and manages traffic once it's inside. Understanding that boundary is critical. It's what allows you to design systems that are resilient, scalable, and aligned with how real-world platforms actually operate. Running the Gateway API in production unlocks a set of operational patterns that simply weren't possible before. It gives you a level of structure and intent that traditional Ingress setups struggle to provide. You can run multiple gateways side by side, each one representing a different class of traffic: public-facing, internal-only, partner-facing, or even region-specific entry points. Teams then attach their routes independently, without interfering with one another or modifying shared infrastructure. This naturally introduces team-level autonomy. Application teams manage their own HTTP route in their own namespaces, iterating quickly on routing behavior, while the shared gateway configuration remains untouched. At the same time, infrastructure teams retain control where it matters most. They own TLS certificates, listener ports, and the overall security posture at the edge of the cluster. The result is a clean balance, strong central governance, without slowing down application teams. Observability becomes critical in this model because gateways represent shared infrastructure. You monitor them the same way you would any edge appliance. Latency, throughput, error rates, and saturation all becomes first-class signals. Security also becomes much clearer. Policies are applied at the gateway level, while application-specific routing logic lives at the route level. This separation makes it far easier to maintain compliance without constraining developer velocity. Instead of stitching together isolated Ingress objects across dozens of namespaces, you end up with a coherent, multi-layered network edge, one that's designed intentionally, not assembled incidentally over time. The easiest way to really internalize Gateway API is to picture your Kubernetes cluster as a modern airport. Not a small terminal with a single entrance, but a large, well-designed hub built to handle scale, complexity, and many different journeys at once. At the top level, the gateway class is the architectural design of the airport itself. It defines the kind of infrastructure being used, what capabilities are available, and how that infrastructure is expected to behave. It's the decision that says, this is the type of airport we are building. From that design, the gateway comes into existence. This is the terminal, the physical building where passengers arrive, and where the outside world first enters the system. Within the terminal, each listener acts as a gate. It determines which flights are allowed through, Or, in Kubernetes terms, which protocols, ports, and host names are accepted at the edge. Once inside, routes take over. They behave like the signage and corridors that guide passengers to the correct destination. HTTP routes direct traffic toward one area, TCP routes lead somewhere else, and gRPC routes guide requests to yet another path. Each one clearly defined, structured, and intentional. At the end of that journey are the backends, the service desks, the operations rooms, the places where the actual work happens. Traffic flows inward through a clean, layered system. Workloads respond, and those responses flow back out through the same controlled path. Seen this way, Gateway API stops feeling abstract. It becomes intuitive, a structured edge, a clear separation of responsibilities, and predictable routing behavior from entry to execution. Gateway API isn't just the next networking object in Kubernetes. It's the next generation of how we design the edge of distributed systems, built for real organizations, real teams, and real world scale. We reached the end of the video. If Gateway API finally clicked, not just the YAML, but architecture behind it, hit like so other engineers can find this breakdown. Subscribe to TechHUB for high-level engineering deep dives and cloud-native design explained clearly. Now tell me in the comments, what's next? Service mesh, envoy proxy, or a live Gateway API demo with real traffic flows? Drop your choice below. Thanks for watching, and I will see you in the next one.